Now we do have another part called tubular secretions, and this part is just for your information only. Okay, only need to know, yes, there is a term called tubular secretion. And what we do, tubular secretion basically is selectively transfer some of the substances from the blood in the peritubular capillary into the renal tubules. Okay, so it means that some of the items that we do not want them to present in the tube, okay, the capillary tube there. So what? Sorry, capillary tube. Capillary. Okay, what we don't do is we pump them into the renal tubule. Okay, so generally happen at the region of distal convoluted tubules. These substances includes potassium ions, hydrogen ions, and including certain drugs, for example, penicillins and also the creatinine, the waste material. And we do know that something to do with the hydrogen ions means we regulates the pH. So if let's say in our blood the pH is low because high concentration of the sodium hydrogen ion, then our body will be able to do this tubular secretion by secreting the hydrogen ions into the renal tubule. Okay. Second one, actually, what we need to know here is the potassium ions. So why call potassium ions so important? Because we need to know, in the next topic, potassium ion involved in the nervous system, particularly transmissions of the action potential. So if the K plus ions concentration is not correct, then you may cause the problem. For example, nerve action potential are not effectively transmitted. The strength of the muscle contraction would be decreases, and decreasing. The heart rhythms become irregular, and cardiac arrest means that your heart may stop pumping. So that's why potassium ion, you cannot be too high. Okay, so what we can do, if your blood potassium ion is too high, then we're going to have the tubular secretion, secrete them into the tubules. Okay, so the diagram here basically summarize the entire process. So the most happening one is our PCT, where you can see that we reabsorb back the sodium and chloride ions, we reabsorb back the nutrients, and also we reabsorb back the most important water molecule. Okay, so sometimes the cell also produce the ammonia. So ammonia is toxic, so we don't pump them, we don't let them enter into the blood, right? So we have the tubular secretions of the ammonium ions into this PCT. Okay, and majority of the water molecule actually reabsorbed back by osmosis, okay, into the tissue fluids at TCT. And we do know that when these filtrate enter into the descending limb, and the descending limb permeable to water molecules, therefore water molecule will be reabsorbed back, and ascending limb actually is involved in these reabsorptions of the sodium and chloride ions. So when the filtrate continue to go around and enter into the DCT, when enter into the DCT, then again the first part we continuously reabsorb back the sodium and chloride ion, making the filtrate dilute and then high water potential, so that the second part of the DCT we will be able to reabsorb back the water molecule. And when this filtrate enter into the collecting ducts, you can see that it's going deep down into the medulla regions, where we are continuously to pump out the sodium chloride ions. But at this moment, you can see that water molecule also will be reabsorbed back. And urea, in this case, also reabsorb back, because when we reabsorb back the water molecule, the concentration of urea keep on increasing until a certain critical point, then the very steep urea concentration gradients is generated. Therefore, urea also can be reabsorbed back. But again, I say that urea is not something that we want to reabsorb back, but we have no choice to reabsorb them back because we reabsorb the water molecule, making the concentration of the filtrate is high. Okay. Now you look at this diagram. You look at these diagrams. Okay, it's a relative. It's not the correct concentration. It's relative to the filtrate. Okay, and from this diagram, we need to explain some of them. Okay, first of all, look at the amino acid and glucose. Okay, both of them, right? Okay, enlarge. So amino acid and as well as the glucose. So relative concentration, you can see that almost zero concentration. Why? Because in a healthy person, amino acid and glucose will be completely reabsorbed at the PCT. Are you clear? Okay. So next, we look at the potassium ions and the sodium ions. Now, again, be careful. It doesn't mean that potassium ion and the sodium ions, they have the same concentration. It's a relative. Where we compare to the number of times greater than the concentration in the renal capsule. So basically Bowman capsule. So everyone start with 1. Okay, because why? If let's say, for example, when you we have the ultrafiltration. Okay, ultrafiltration. So let's say I ultrafiltrates, okay, ultrafiltration 100 units take place. And at this moment, it's still 100 units. So 100 over 100. So you get 1. But if I reabsorb them back already, okay, when I reabsorb them back, then it will become less than, let's say I reabsorb 90 of them. So out 100, let's say I reabsorb 10, sorry. So it becomes 0.9 and so on. So therefore, it's not a real concentration, it's a relative concentration. Okay, don't read this diagram wrongly. Sorry, let me remove this one. Okay, so now, so means they compare to what? They compare to the initial concentration, how many fold greater. Okay, so in terms of glucose and amino acid, because we already reabsorb them back, so you can see that in the PCT, after PCT, you won't see any trace of the glucose and amino acid. Now, how about sodium potassium ions? Sodium potassium ions. Now, even though we reabsorb the sodium ions, correct or not? We absorb sodium ion, we absorb the potassium ions. But the thing here is, during this part of the process, okay, sodium ion concentration remain constant because due to this concentration of the sodium ion equal to mass over volume. So mass decrease, volume also decrease. Both of them decrease. Why volume decrease? Because we reabsorb back the water molecule. So therefore, sodium ions remain relatively constant. It won't change in terms of the concentration. Are you clear? So you can see that remain constant. Okay. Then how about why form a loop here? Because we know that loop of Henle actually have the descending and ascending limb. At the descending limb, you can see that the concentration of the sodium and potassium ion increases. Why increase here? Because water molecule reabsorb back. So look at the formula here. When the volume of, okay, this is a descending limb of tube of Henle, volume decreases, mass no change. So therefore, sodium and potassium ion concentration now increases. Okay, clear or not? But after that, this part is the ascending limb. At the ascending limb of loop of Henle, we continuously pump out the sodium ions. Clear or not? So making the concentration actually drops now. Okay, and you can see that after that in the distal tubule and collecting ducts, concentration now increases. Okay, why? Because we do know that in the DCT and also the collecting ducts, we reabsorb back the water molecule, making them actually back to normal. But potassium ion, you can see that increase even more. Can you see that? Why? Because at the DCT, the effect here not only because of the reabsorption of the water molecule only, but also the potassium ion, particularly here due to the tubular secretion at the DCT. So because of the tubular secretions, therefore concentration of the potassium ion even higher. Okay, urea keep on increasing in this case because of reabsorptions of the water molecule, making their concentration become higher. Nothing to do with reabsorb of urea or what we actually add on the urea there, but basically due to the water molecule that have been reabsorbed back. Okay, so again, I go through the answer with you guys. Quick one. So amino acid and glucose are all reabsorbed back into the blood from the PCT. Okay, so therefore after this, you won't be able to see any trace of the glucose and amino acid. How about urea? So a low concentration of urea is reabsorbed in the PCT, but its concentration increases because there is now less water present. It means a low volume. As more water molecules reabsorbed through the loop of Henle, the concentration of urea continue to increase. Not only loop of Henle, but also the DCT as well as the collecting duct. Okay. So how about sodium potassium ion? So although both sodium ion and potassium ion are reabsorbed in the PCT, their concentration does not change because water molecule also reabsorb back. The concentration of both increase as they go down the descending limb of the loop of Henle because water molecules are lost from there by osmosis into tissue fluids around it. So as the tissue fluid passes up, the filtrates, okay, passes up the ascending limb, sodium ion are actively pumped out, so their concentration inside the tubule actually decreases, okay? And because we do know that DCT and collecting ducts will reabsorb more water molecule, so therefore both of them increase in terms of their relative concentration, but potassium have higher because of the we actively transport them into the distal convoluted tubule. So this one actually is a tubular secretion. Okay, due to the tubular secretions. Okay, so which explain why the concentration rise more than that of the sodium ions. Okay. So you look at compare the substances that enter into the Bowman capsule per day. So we calculated it's about 180 liters of the water have been filtered into the Bowman capsule, but reabsorbed by about 178 to 179 liters. Therefore, you can see that in urine only 1 to 2 liters only. How about glucose? You can see that this is the how many grams of the glucose filtered per day, but we reabsorb all of them, same to the small proteins and also amino acid. It cannot be large protein because large protein, if enter into Bowman capsule, that is indications of the kidney failure or the kidney infections due to the kidney inflammations. Okay, so this protein, you cannot find any large protein in the Bowman capsule, okay, or plasma protein. And we do know that, can you see that? Okay, one thing here we did is not in our syllabus. Small protein, how we reabsorb them back. Small protein, we can reabsorb them back at the PCT. Okay, small protein is reabsorbed back at the PCT by the process of endocytosis. Are you clear? Endocytosis, but not all proteins. Okay, small protein normally can. Okay, small protein normally no problem by endocytosis. So generally, you won't have the small protein in the urine. Okay, sodium and chloride ion, yes, we reabsorb back majority of them, but not all. Okay, so you can see a trace of the sodium and chloride ions. Bicarbonate ion also, you can see some trace of this. Potassium ions, okay, potassium ions, you can see that we ultrafiltration take place, 29.6 grams appear in the Bowman capsule, but reabsorb back also 29.6. But how come still have 2? So write down this is because due to the tubular secretion. So if question asks, so the answer is because of tubular secretion. That's all. You do not need to know what is the mechanism. Okay, so that's why I also, because it's quite complicated, so I didn't put it in the notes. Okay. So, and then urea, out of 54, we reabsorb half of them. Can you see that almost about half of them will be reabsorbed back because of the dynamic, okay, equilibrium. Okay, reach a dynamic equilibrium, so therefore about half of it we will reabsorb back. Then creatinines, we cannot reabsorb the creatinine at all, so 1.6 gram. Creatinine, we won't be able to reabsorb them at all because we don't have the special transport protein. Okay. So